Hello! Number 7 in the wave nature of light, Snell's law. Now, who's Wilbrund Snell? 1591 to 1627. That's who the law is named after. That's what he looked like when collars were big. And he discovered that the refractive index of a substance can be found using the angles of incidence and refraction. And this is what's referred to as Snell's law, and there's a variety of forms of Snell's law, but they're all basically saying the same thing. And this is one way of writing it, where the sine of the angle of incidence divided by the sine of the angle of refraction equals n, the refractive index. Now, there is always some confusion between the difference between an absolute refractive index and a relative refractive index. So as we go through this, I'll try and make sure we're clear on this. Now, this is just the general formula for a refractive index. The difference between an absolute refractive index and a relative refractive index depends very much on whether air is involved. Let's do an example. Light from a light box is shone onto a block of perspex at an angle of 30 degrees to the normal. Determine the angle of refraction. And we know, and in this case we're given the absolute refractive index of perspex 1.4. Now this is a value that relates the velocity of light in air to the velocity of light in perspex, and so that's a constant, or a vacuum. I said air, but it can be a vacuum as well, because basically we assume that light travels at the same speed. It's only if you get into some particular physics experiments that it makes much difference. So here we have Snell's law written in this form, where we're given the angle of incidence, which is 30 degrees. There we are, we put it in there, we divide by 1.4 and we get that angle. Therefore the angle is 21 degrees. So in this case it's going from less dense to more dense, and therefore the angle of incidence is greater than the angle of refraction because it's being bent towards the normal. Should be able to do some questions in your workbook now. The relative refractive index for light passing from one medium to another medium is given by this equation. Okay, and this is only in the context of the transition from these between those two mediums. So not to be confused with the absolute refractive indices, which are these guys. Therefore, a more general form of Snell's law is the sine of the angle in medium 1, sine of the angle in medium 2. So it's going from 1 to 2, and I like to draw a little arrow in there. So this is showing that it's going from 1 to 2, because we might look at this situation where it goes from 2 to 1, in which case all this has to be reversed. And therefore it's written like this. Yep. And remember that N1 and N2 are the absolute refractive indices, and you would more than likely be given those in the question or in a table, and you would be given one of these angles. So on our formula sheet, again, it's written slightly differently again. Instead of I, they use theta I and theta R, incidence, refracted, incident, refracted. So this is the velocity in the medium 1, velocity in medium 2, and this would be the absolute refractive index only if this was air. If this is not air, this is a relative refractive indices, just to confuse you even more. And then it's restated like this. So let's do an example. Find the angle of refraction for a ray of light passing from water to glass when the angle of incidence in water is 25 degrees. That means it's going from water, well, it's hard. I would say the water is less dense than the glass, and we're using this form of Snell's law, and they've used subscripts here for the water. This is what it's incident in, this is what it's refracted in, so this is the glass, and they're using 1.33 and 1.5 are the absolute refractive indices of water and glass. Where do they get them from? From a convenient table, but they would normally be given to you in the question. And then it's just a matter of using your calculator, making sure your calculator's in degrees. So you should be able to do a whole lot of questions that are very similar to that, just being careful about what we put and where. And in the next video we'll actually look very quickly at dispersion. See you.